Now look at this one. Maybe it takes some time for you to remember this. It's done a long time ago. Now these questions are level 1 in integration with substitution, but I want to talk about how I solved 24 and 26. So my suggestion is that even if you got it correctly, you still should write down. You still should take notes. So 24. Integral log x to the power 4 log x to the power 4 I'll write 1 over x dx together. And then there's a substitution. Now this is a substitution without using the new variable u, but in fact you're using it, but you're not writing it out. That is 1 over x dx equal log d log absolute value x. And in this case, because we know that in this question x is positive, so I will just remove the absolute value. Only in this question, we can do so. And then in the end is 1 over 5 log x to the power 5 plus c. The highlighted part is the substitution. Now, when I marked your work, some of you shown that you're not 100% complete. You're not 100% sure that this can be done. So I saw some of you are doing differentiation. You don't have to show that anymore. Our ultimate goal is for you to be comfortable with this kind of substitution, and you can do it immediately. So that is 24. Now please take down notes, okay? If it's not entirely the same as yours, you write it down. You write it down. Question 26. Now you see the standard solution, the given solution by the textbook. It's rather short. It's very short. So I want to give you a longer version if you're not so sure. Again, when I marked your work, I saw some of you with different methods. If I put down in your homework book and I say it's correct, then it's correct. But if it's wrong, if I underline something, it means it's not 100%. It's not 100%. And here is my suggested solution. This is similar to the previous question. And then I will do this. Now this is very similar to the previous one. I will do this. 1 over x dx is d log absolute value x. Similar to the previous question, because in this question we know x is positive, therefore I can remove the absolute value. Okay. Now, still you have the coefficient 4, and inside you don't have coefficient 4. How do you do it? There are two ways to solve this. Now, one of my suggested solution is to copy 4x, and in here you're adding log 4. Now here, by adding a constant, you're not changing the value. You're not changing the value by adding a constant. And then by the log property, you will have d log 4x. That's why in the end, the given solution is 1/2 log 4x squared plus c. Okay. Now I'm after work. I didn't see anyone show me all the steps, but I did see that some of you are getting this result directly. Now from here, some of you are getting this result directly. This result directly. Now, of course, some of you showed the why they are equal, right? They showed me exactly why they're equal. Some of you didn't. Like the standard solution, it doesn't show why you can change 1/x dx to d log 4x directly. It doesn't show. To me, it's not so obvious. I think to you, it's not so obvious either. So this is one way to see it. That 1/x dx is actually d log 4x as well. Is that okay? I also mentioned that there is another solution. I saw this solution from 2 different students. So if you allow me, so from here, I can also go another way. So instead of by adding log 4 there, I can also go the other way. I saw that in your solution on this one, is that some students figure out this is just log 4 plus log x. Instead of adding log 4, you can also split log 4x to 2 logs, log 4 and log x. Okay. That in this case, you will get a different answer because this will be log 4 times log x plus 1/2 log x squared plus c. Okay, and that answer is also correct. This is also correct. Now, if you compare these 2 answers, I hope you can find peace. Oh, these are equal, equivalent. But what I do not want to see is that some of you are using this method but get this answer. I don't know how that's possible. No. But some students are using one method and get the other answer. I don't know how, unless there is some messed up things going on. So that is 26. I hope this will make you see, if you didn't see it before, if you have to use another variable u, maybe this is a way for you to avoid doing that. Because we do want to get the result faster. Is that okay? Let me know. Let me know. Now you have some time to check the other assignments. 1 minute for me to get ready as well. Okay. Okay. 1 moment. Can you see the file? Hello?
Yes.
Can you see the file, girls?
Sorry, Miss Chen, I don't think we can see the file on your screen.
Yes. So now if I cannot see it here, I will I'll find it somewhere else, okay? This is the assignment number 3 in this chapter. I also today, just now before the lesson, I returned this assignment to you as well. Gladys, you cannot see the file. I mean, if you open it in your device, because I uploaded. Okay. Okay. Then this one, I think it's difficult with the 32 and 34. I don't know. I think 32, 34. So let me show you again what should be done. Now, in my standard solution, I show you the way of using the variable u. I think it's easier to use the variable u in this case, because otherwise you have to do a lot of arrangements. But in this solution, I'm going to show you the way that you don't have to use the letter u. I don't know. On the one hand, I want you to be able to do both. Now, in this case, definitely it's recommended that you let u be 2x minus 1 in this case for question 32. Definitely this method is easier. But I'm also going to show you that, because we can do it without. It's also possible. It's just harder. And I saw that in some of your, when I marked your homework, I saw some of you did that. And now I'm just going to show you how. Please take notes. If you don't know how this is done, please take notes. For 32. Two x plus 1, 2x minus 1 dx. Okay. And this is equal 2x minus 1 plus 2. 2x minus 1. And that is equal 2x minus 1, 2x minus 1 plus and that is equal to 2x minus 1 2x minus 1 okay, and that is equal to, how do I put it, 2x minus 1 1 over 2 dx plus 2x minus 1 negative 1 over 2 dx. Okay, and this is equal to, now this one is 1 over 2x minus 1 1 over 2 d 2x minus 1 plus 2x minus 1 negative 1 over 2 d 2x minus 1. Now the substitution, let me highlight the substitution now. Until this step, before this step, I haven't done any substitution, but this is a substitution. That is 1 over 2 d 2x minus 1 is replacing dx. Now for the second one is 2 dx is replaced by d2x minus 1. I hope you see it. Maybe I should use a different color. This one replaced by this, and dx replaced by the previous one, okay? And then 1 over 2, I think it's 1 divided by 3 over 2, and 2x minus 1, 3 over 2, plus 1 divided by 1 over 2, 2x minus 1, 1 over 2, plus c. So the answer is 1 over 3, 2x minus 1 to the power 3 over 2, plus 2 times 2x minus 1 to the power 1 over 2 plus c. And then it's done. Okay, now we have these two methods side by side. I hope. Yeah, you have them side by side. You can see this one is much shorter. Right, and it's not a very difficult substitution. It's not. In terms of calculation, I think they're equivalent. The calculation, they're equivalent, but this one is just much shorter to write. And also you see when I used the substitution, I changed the variable x to the variable u entirely. That means everywhere. In some of your homework, I still see you use a mixture of u and x. I hope that can be avoided in the future. That just shows the maturity of your skill. If you can, because it's like a middle product of the substitution. If you can do the substitution completely, that's better. It's just I'm not saying you're wrong. It's just not ideal to present it that way. You see the suggested answer, there's no mixture of u and x. That's 32. That's 32. So that took a long time. But this part, to add 1, sorry, to minus 1 and add 2, I hope you see that coming. Okay. 32. Now 34, if you want to use the same method, it's even harder, but I'm going to show you again. 34. You need to write it down. You need to write it down. But this one is not easy, not easy. Without this, now this method definitely better, but without the use of u, then look here. Now first I need to divide and then multiply. That's simply because I need a 3 in the coefficient. So I will multiply and divide. Okay. And then I'll consider minus 1 and plus 7. You see, 3x minus 1 plus 7 divided by 3x minus 1 squared 2x. Otherwise, there is no, you can't do the same thing as question 32. You cannot do the same thing. That is a very good move. Sorry. Correct? And then that is 1 over 3. Seven over 3. Okay. Then the next part is the change of variable. And then the change of variable. I hope you can see that. This and this. Change of variable. And then integration. And then the final answer. It looks better, don't you think so? Again, if you compare them, this is much shorter. It's almost the same. In terms of the integration part, it's almost the same. You're integrating the same function. Do you see? The one is with you, the other one is without you. if you have enough practice, then this will become easier to you. But I'm happy to see that after a few weeks, I think a lot of you are getting better though, for some reason. I believe that you did a lot of practice though. I think you have done a lot of hard work. Moving on. I wanted to explain 41, but I don't think now it's necessary because just now we worked the 24 and 26. So they're very similar to this one, although in my standard solution, it's not very long. The steps are not all given. I hope you can figure out yourself. Okay, this one. Let's move on to the last assignment. You have to give me some time. I don't have the preview. I think you can still, you must be able to download, but I will just get my original file. Now this one I'll erase now. I'll erase now. For the last assignment, let me see what should be. What is there to talk about? Not much with the substitution, because in this part the substitution is not the hardest part. The hardest part for this assignment is the identity, the trigonometric identity. So let me see. Now for all of you, I still, if you look at the standard solution, there's no use of and the other letter U. We're not using it anymore completely. You cannot see it anymore, right? And some of you are still using it. I hope you don't. I hope you don't have to. Like here in question 29, this question, I hope that you can easily get cosine dx is d sine x. Sorry, I misspoke. It's cosine x dx can be replaced by d sine x. I think that's very obvious to you now. Unless you don't think so, because I saw in your homework, I saw that some of you are not completely sure, like don't know. Don't know you can do that, but you should be able to. And the other one is secant x squared dx equal d tangent x. This is the other one. Secant square x dx equal d tangent x. That part is used in question 30, right? You can see the power 4 become power 2, and dx is changed to d tangent x, right? There shouldn't be u something, shouldn't be, right? I don't know. You let me know. In question 42, you use the double angle formula, but backwards. That is to increase the angle and reduce the power. Luckily for this question, a lot of you use the same method. So for me, the marking is not so terrible. This is the correct answer, okay? Please check your homework. Even if you got the full mark, doesn't mean you're completely correct. That's all for the homework. Let me close the file and open again because I don't know why it says orphan here. So I will close the file. Now today we're going to do more integration. And this part is a new technique. This is a new method that is used on a very specific, a bunch of specific function. Only using this method you can solve it. This is called it's a substitution method. It's used as very, I'll talk about that later. It's a substitution, right? It's a substitution. So before this, I want to introduce a new kind of function. You may be surprised that all the functions we have learned are not enough. We have this and that and this and that is not enough. Not enough when you have to do integration. Not enough. So let me introduce this new type. It's called the inverse trigonometric functions. You have seen them, but you never learned them as a function. You've learned them as an operation, not a function. Now in this function, you can see the symbol of the function is just say sine inverse. Now it means that on the left, you're getting the angle, and on the right-hand side, you're putting the value. So you're putting the value of sine inside the inverse function, and the outcome is an angle. Okay, for example, I can put, for this one, I can put sine, let's say 0.5 inside this, right? And then I should get an outcome. The outcome is an angle. Now, if you know about trigonometry, you should know that a lot of angles have the same sine value, the same value. But for this one, the outcome is only one angle, not multiple angles, although all of them share the same sine value. For example, this one, the outcome is 30 degrees, or you can say pi over 6. Of course, the outcome, I mean, if you think about the sine function, the sine value, the sine 150 degrees also has sine value 0.5, but the outcome is not that. The outcome is pi over 6, precisely pi over 6. That is because we also, when we define this function, we also have defined the so-called the range of the function. Now, the range of the function is called the principal value. It means that no matter what value you put inside the sine, the inverse sine function, the outcome must be an angle between negative 90 degree to 90 degree. You're not supposed to get 150, although 150 also has the same value. You only get the outcome that is from negative 90 to 90. Now this is based on the sine graph. Now in the sine graph, this is 90. This is negative 90. Okay. Now, whatever value you put in, let's say I put in 0.5, you're supposed to get this angle, 30 degrees. You're not supposed to get this angle, 150 degrees, because that's not the principal value. The principal value is between negative 90 to 90 degrees. Now, this is the principal value. For the same reason, if I input negative 0.5, I'm supposed to get negative 30. I'm not supposed to get these angles. This is another angle here. Also, there's another angle here. A lot of angles share the same negative 0.5, the sine value, but only one is the outcome. Now, luckily for you, this principal value is already put in your calculator. So whenever you use your calculator, remember that your calculator only gives you one angle. That is always going to be the principal value. So if you don't remember what the principal value is, you can put a number inside, then in your calculator, the calculator always tells you the principal value. Is that okay? Now for the cosine, also you input the cosine value, the outcome is an angle. But for cosine, the principal value is different. This is because for the cosine graph, the cosine graph looks like this. The principal value is from 0 degree to 180 degree. Although there is graph on the left, but those are not the principal value. Now these are not the principal value. Maybe I shouldn't use, like, let me use a dotted line. So if you input, let's say this value 0.5 inside, you're supposed to get 60 degrees. If you put negative 0.5 inside, you're supposed to get 120 degrees. So the principal value is between 0 and 180. This is the principal value. This is also put in your calculator. It said so. Whenever you put, you want to type in, if you type in inverse cosine 1, you will get inverse cosine 1, that is 0 degree. If you put inverse cosine negative 1, you will get 180 degree. Although this is also the negative 1, you see, the negative 180 also give you negative 1 cosine, but the outcome is the principal one. The principal angle is 180 degrees. Now this mustn't be confused with the so-called the reference angle. Girls, I almost regret to discuss this with you. The principal value is not the same as the reference angle. I'll just leave it there. I'll just leave it there. If you recall what we did when we solved the trigonometric equations, we always use an angle that is in quadrant 1 as the reference angle, and then use your brain to find all the other solutions. That angle is called a reference angle. Okay, Now, in this case, especially with the cosine, also with sine, you can see sine can be negative, you see? But in the reference angle is not negative. I think enough said, not the same. Now with the tangent, it's the same as sine. It's between negative 90 to 90. Now, do you have to know that? How well do you have to know this? Depend on how much you want to use it. I would say in our textbook, in our range, if you don't use it too much, then this is okay. Then I think knowing what the symbol is okay. If you don't try to or use the angle and try to use it to prove identities, then knowing what it is okay. Whether or not you need to remember the principal value, let's see through the example, like whenever you need to use the principal value, let's figure out, because in my experience, it's not so much involved if you don't dive really deep into this concept. Okay, so that is the new type of functions. It's actually the last type. I think it's the last type. There are these functions there, those are called the basic functions, I think. And basic functions, there are 6 types. I remember there are 6 types, and this is the last one. I think this is the last one, but it's not in our textbook though. This is the last one. All the other ones we have covered. That is the polynomial, exponential, logarithm, and logarithm and trigonometry. This one, inverse trigonometry, is the last one. Anyway, that's it. That's it. As to the integration part, it's just sometimes the functions look so weird that it's not possible to solve it. I'm just going to tell you that these functions cannot be solved any other way than this particular, the substitution. And you have to use the substitution, otherwise it's not possible. It's just not possible to be done. Do you believe it? Now, for example, this is very simple integration. Example 25. Now you can try let u be something. You can try the previous method. You can let u be this, let u be that, let u be this, then that. It doesn't work out. What I can tell you now is it doesn't work out no matter what you do. But this substitution will work out. It's weird that way. This substitution. So now to save time, I will tell you that any other method will not work. If you don't believe me, you are welcome to try. You should try, in fact. But to save time, any other method does not work. Now, what you need to do is to use this substitution. That is, let x be 5 times sine theta. Now, in the past, I will write down the principal value for theta because that's just correct. But you don't have to follow me. That this is not necessary. But if you want to, you should write the principal value. That is, theta is between negative 90 to 90. Theta belong to, I use this one now because we learned it very recently. Theta belong to negative 90 to 90. Now here I also change 90 to power 2, 90, close bracket. Now here I do not use the closed interval because the denominator cannot be 0. I hope you see that. If it's equal to 90 degrees, then x equal to 5, and that is not okay because x cannot be 5. In this case, only in this question, I will not include the 2 endpoints. But if you include the endpoints, not a big deal. As I said, you don't even have to do this. This is optional. This part is optional. This is optional. Okay. And then I will do the substitution. Now this time the substitution is a little bit different. Wait to see if you can spot the difference. Now I have all the things in x. And I suddenly change all of them to theta. That's my substitution. Do you see the difference with the substitution? Now, the only substitution I did here is this one. I changed dx to d. Now, this is different from a previous substitution, is that this one is so simple. You know, I just replace x with 5 sine theta. It's so easy to do. But in the past, I always have to manipulate and then change something to du in the past, because it's not always dx equal du. It's something times dx equal du. But this time is not. This time is dx equal d5 sine theta. It's easier this way. It's easier this way. Now what you need to do, perhaps you don't notice that I have to do differentiation now, because for this one, that is 5 cosine theta d theta. I think the real substitution is here. Sorry. The real substitution here happens here. That if you see this d5 sine theta is changed to 5 cosine theta d theta. That is also substitution. Do you see? Okay. And for this one, it's 25 cosine square theta. Okay. I'm just simplifying. For the denominator, I'm just simplifying. Okay, now my next step. Now, my next step is the only time that you're using the principal value, because when I take the square root, I need to decide, should I take the positive root or the negative root? And in this case, I should take the positive root. You see how this is intricately linked? It really works out this way. Now, because my principal value is from negative 90 to 90 degrees, therefore, my angle lies in quadrant 4 or quadrant 1. So in that case, my cosine value is positive in quadrant 4 and quadrant 1. Therefore, when I take the square root, I should always choose the positive root. Do you know what I mean? Otherwise, I have to put a negative sign in front. It really is helpful that way. It really is helpful. So it works out this time. You get d theta. And this function become 1. You don't have to write it. The 1 you can just don't write it. And then if you integrate this one, that's theta plus c. Okay, so integration is done. Now in the end, you have to change it back to x. You change it back to x. And to change it back to x, you have to do because x equal 5 sine theta, therefore sine theta equal x over 5. Therefore, theta is actually the inverse of x over 5. The inverse of the sine value x over 5. Now, you also read it as arc sine x over 5. Wow. And then this question is completed. So, to answer my previous question, how well do you have to know the principal value? Just enough to know that this should take the positive root. I think you should know that, don't you think so? If it's if this take negative root, we get a different solution. Do you know what I mean? So that's probably. A similar question, probably. Similar question. For this one, I will let x be. In this case, you see 9 and 4, so I need to, in my head, I need to make it a coefficient that could help me. Like in this case, it's 5. Right, 25 is 5 squared, and this one should be 3 over 2 sine theta. And should I also mention that theta is from negative 90 to 90? In this case, I should include negative 90 to 90. Include. Again, it's optional. Girls, these are optional. In your textbook, you can still see it though. I believe in your textbook, this is written down. But maybe if you're reading the textbook all by yourself, you may not notice the importance of this value. You see, the replacement is done very quickly. The replacement is done very quickly. Just put it in. Put it in. And then this one is the real substitution. That is 3 over 2 cosine theta d theta. That's the real substitution I must highlight. Like in the past, do you have to notice that this didn't happen before? I never have to differentiate this here. Now you have to. You have to. This is a substitution. No, this is substitution. And then simplify. This is 9 cosine square. This 3 over 2 cosine theta d theta. And then again, this is like magically works out because in quadrant 1 or 4, this takes positive root. 3 cosine theta, 3 over 2 cosine theta, d theta. And then I will have 9 over 2 cosine theta square, d theta. But this is not as simple as the previous question. Here it's far away from the answer. For this one, I will change it to 1 plus cosine 2 theta divided by 2 d theta. So that will be 9/4. 1 plus cosine 2 theta d theta. So in this case, it's 9/4. This one is theta. This one is 1/2 sine 2 theta, close bracket, plus c. Is that okay? I skip a little step here because this is 2 theta. I still have multiply 2 divided by 2, that kind of substitution. But because I hope you're fine with that now. This is another substitution. There's a 1/2 involved. Anyway, that's my answer with theta. That's not the final answer yet. That's not the final answer. Now, right now, I have to change it back to x. So this one is 9/4 theta plus 9/8. That this one is sine 2 theta. But instead of sine 2 theta, I will write sine theta cosine theta times 2. So that is 2 sine theta cosine theta. Now, why do I have to do that? Because do I not think this is simpler? You will see. You will see. Because this can be replaced by x easier. Look here. Now, because x equals 3/2 sine theta and 2x/3 equals sine theta, right? So this one, 9/4, is the inverse of 2x/3. That's my first one. Okay, now for this one, it's 9/4 times sine theta. The sine theta is 2x/3. That's sine theta. Now, how about cosine theta? The cosine theta can be found using the sine theta. Okay, now because cosine theta squared equals 1 minus sine theta squared, that is 1 minus 4x squared over 9. That is 9 minus 4x squared. Therefore, again, I have to take square root, and this time I also take the positive root. You see, it's everywhere. The principal value is everywhere. I will take the positive root. Now, girls, please don't try to use this in any of the proofs of trigonometric identities, because those identities are supposed to work for all angles, not just the principal angles. Now here, because our angles are principal angles, therefore I can take square roots on both sides. Now, this method does not work for identities, okay? Only in this question, cosine theta equal to the positive root. So in my question, I will replace it with a positive root and plus c. So really final answer. x/2, 9 minus 4x squared plus c. And then it's finished right now. Have I touched on everything?
I'm not really sure why we have to take the positive root. Like, I don't really understand.
I think so. Now with the classwork, because it's so difficult to get it correctly, so I provided the guide. Now you can finish this and let me know. Okay, this is the easier one. Now this is like part A. Now here I require you to write the principal value. where theta belong to something? Let me know when you are done. Let me know. Let me know when you are done. Raise your hands. Okay, let me show you my answer. In this question, of course, I should use the substitution. I must use the substitution. Let x be three sine theta, and theta belongs to negative 90 to 90 degrees. That here I did this first, so dx equals 3 cosine theta d theta. I did this first, so that in my substitution, I'll just replace it entirely like that. And in calculation of the square root, now the square root cosine square is cosine, positive cosine. Now here we take the positive root because of the range of theta. Because of the range of theta. And then theta, and then replace theta with the inverse sine function. Sophie, can you speak up, please? Because I don't know your question.
Sorry, Miss Chen, can you hear me?
I cannot hear anything. Sorry, I think I'm using my headphone. Can you speak up, please?
Hello, Miss Chen, can you hear me?
Yes, now, right now.
Okay, thank you. So Miss Chen, actually, I have two questions. May I ask for the first question, is it the principal value always the same for every question, like regardless of the question type?
Yes.
Okay, thank you.
The principal values are decided when we make up the so-called inverse trigonometric function, and it's already decided. It's everywhere. It's everywhere in your calculator and in textbooks. They are all using the same one, but you should pay attention in that sine and tangent, they have the same principal values, but the cosine is different.
Thank you, Ms. Chen. And my second question is that I still don't really understand why we have to take the positive root, but not the negative root.
This is because, let me use this one as an example.
Thank you.
Now, in the classwork, I think it's easier with the classwork, is that perhaps I skipped something. Is that in the function, in the original function, this one, original function, although we never say anything, but if I ask you what is the domain of the function, you should know that x is greater than -3 and smaller than 3, the domain. X greater than -3, smaller than 3. Otherwise, x squared will be greater than 9, and that will make the square root imaginary. Let me repeat. Because we want the x squared to be smaller than 9, so the range of x, i.e. the domain of this function, is between -3 and 3. Otherwise, this will go imaginary. Do you get what I mean?
Yes.
Okay. Now, if x is between -3 and 3, then when we assign this function to x, we let x be 3 times sine theta. We really don't need theta to be all the real angles, do we?
No
We don't want theta to be all the angles. We only want a few angles. Why is that? It's because in the graph, this is the sine graph. Now, the sine graph between -9 and 9, that is here, between -9 and 9, sine value already goes from -1 to 1. Let me repeat. Between -90 to 90, sine theta already goes from -1 to 1. Now, so in this question, if we want x to lie in -3 to 3, then we only want theta to go from -90 to 90, and that will cover all the values for x. It's not mentioned, but you should think that. If we want theta to be every other angle, any real angle, then that's too many. We only want a few, that is between -90 to 90. Now, because of this requirement, so in the end, when we have this, now in this case, when you do the calculation in the process, you will get square root 9 cosine squared, and that is equal to 3 cosine square theta. And because we know cosine theta is positive, in this question, cosine theta is positive because theta lies in quadrant 4. And then I should say, oh, this is equal to 3 cosine theta. Otherwise, it's not.
Ms. Chen, but can it be -3 instead of +3?
Say?
Like, can it be -3 times cosine theta, but not?
No. Because this surd must take a positive root, this value is defined as positive. So the outcome must be positive, and this is a positive value. If you write -3 cosine theta, that is a negative value in this case, in this context.
Oh, if it's negative, then we have to add a negative sign in here, like here.
Yes. Because
Okay.
at the beginning, it doesn't have a negative sign. So in the end, it shouldn't have a negative sign.
Thank you, Miss Chen.
Okay. Now, the same reason you do it here. Because in the end, I want to express cosine, right? Here in the answer, it has cosine in it. And I want to replace cosine with x. So I have to figure out what cosine is. And we know that cosine square equal this, but what about cosine? It can be positive or negative. If we allow all the angles for theta, if we don't require all there to require theta, that theta belong to the principal value. If we don't have this principal value, then theta can be anything, then cosine theta can be positive or negative. Then here we do not know which value to take. But luckily, in this question, because we have a principal value, so when you have cosine, you always take the positive root. You don't have to consider, oh, is it positive or negative? It's always positive. So that is the tricky part of this. That's the tricky part of this. Now, as I said, do you really have to know this in detail? For the first lesson, you try, because in the end, you will find that it's always positive. It's always positive, means that you don't have to consider the negative case, because it's never negative. The beautiful part of the principal value is that once they are decided this way, then every time you work it out, it's positive. Like in these two questions, right? Whenever we have to figure out cosine, because cosine is always positive in this case. So you never have to take the negative root. So in a shortcut, you can say, oh, I don't have to consider the negative root. You can also say that. But to really understand why the negative root is not there, it's another story. It's another story. You have to look into the rationale behind the principal values. Now, I'm happy to discuss with you way more. It's not easy to grasp. This is quite deep. It's not easy to grasp, but the main thing here is not about that. The main thing here is this. In our lesson, the main thing here is what I highlighted here, not this part, not the theta, this part, but the replacement, the substitution. If you can do the substitution, then you're fine. Okay. I'll show you another one. In example 23, that this cannot be solved. This is another example of, it's just I changed the function a little bit, and then it cannot be solved unless you use this substitution. You have to use this substitution, right? The sign substitution does not work now. You have to use the new substitution. So in this question, I will let x be 3/5 tangent theta. And here theta is between -90 to 90. I'm just writing down I'm just writing down the principal value for tangent. Principal value tangent. The principal value for tangent is equal to the principal value for sine. It's just that the -90 and 90 are not included. Sorry. The -90 and 90 are not included. That is because, not because of the denominator or anything. In the previous example, it's because the denominator cannot be 0. But in this case, it's because tangent theta cannot be, tangent 90 degree does not exist. That will naturally give you theta belongs to the open interval without the two endpoints. Okay, so different reason for not including -90 and 90. Moving on. Now we can do the differentiation now. That is dx equals 3 over 5 secant theta squared d theta. So that my substitution can be smoother. Right? And then 3 over 5 secant squared. Right? And then this one is just 9 secant theta squared. It just worked out that way. It's like this function is made for this substitution. It's just only this one will work. And then you would delete that. You will get 1 over 15 d theta. That is 1 over 15 theta plus c. Okay. Again, you need to work out theta. So here, because x equals 3 over 5 tangent theta, therefore tangent theta equal 5x over 3, and theta equal the inverse of 5x over 3. So my final answer is this, 1 over 15, the inverse tangent. Let's see. Is that okay? Now, in this question, we do not discuss what is so useful with this because it's a square. You don't have to take square roots. So you don't really have to decide, oh, is it positive or negative? But it's not. Something may happen. Something may happen. Later on, you may find yourself deciding what sign to use. You do the classwork. You do the classwork and show me. Let me know when you're done. Okay. Let me show you my answer. You use the correct substitution. In your homework, you have to decide the substitution yourself. Now you can kind of sense what the substitution is if you have 16, right? You have a 16, you think about 4. Okay, 4 will work. And then when you do the substitution, it's a good habit that you know what theta is, because theta is not all the angles. It shouldn't be. It shouldn't be all the angles. It shouldn't be. Only very specific angles, okay? Now, anyway, if you don't write this, it's not the end of the day. If you don't write this, that's fine. But you have to write this because this is the substitution part. Substitution. And then you do the substitution, you simplify, you get integration. And then you replace theta with the inverse function. Okay. Another example. This is the last example. Part A. Express it as the perfect square. Now we've done this before. It's x squared plus 4x plus 4 plus 7, plus 3. And that is equal to x plus 2 whole square plus 3. Now we've done this before. This is for the vertex form. Can you believe that the vertex form is still useful here? Yes, it is. Yes, it is. Because right now, with part B, with this integration, I will just write it this way. With this integration is very similar to the previous example. I don't know if you see it, but I see them as very similar because I see something plus something square. This should remind you of something. Although these numbers are not very good because I still have something plus something squared. Do you see? I still have something plus something squared. It's just that these values are not perfect square. It's not that good, but still you can do a substitution. That is to let, I'll write it here. Okay, I'll write it. I'll write it here. I will let x plus 2 be root 3 tangent theta. Because I want this to be tangent square plus 1. I want this to be tangent square plus 1. So that's how I decided. So this square thing must be root 3 tangent theta. And theta belongs to negative 90 to 90 degrees. This is optional. Optional. Now, because x equal root 3 tangent theta minus 2, therefore dx equal root 3 secant square theta d theta. Okay, here's my substitution. Root 3 secant square theta d theta divided by, this one is root 3 tangent theta whole square plus 3. And that will give me root 3 tangent, secant square divided by 3 tangent square plus 3 d theta. And I know this is root 3 secant square theta divided by 3 secant square theta d theta. And that is equal to root 3 over 3 d theta. And that is root 3 over 3 theta plus c. Okay. And again, I need to do this back. That is tangent theta equal x plus 2 divided by root 3. So theta equal inverse tangent x plus 2 over root 3. So there's a root 3 over 3 inverse tangent x plus 2 over root 3 close bracket plus c. Again, in this question, the range of the principal value not so, it doesn't seem very useful. Again, you don't know. You don't know. Maybe useful. Can you do the classwork? Okay, can you do the classwork? Now, in the classwork, you must think of the substitution yourself. It's not the same. It's not the same. Not the same as this one. You try. You try. Now, please look at my answer. Now, with the completing square part, I'm not used to the negative sign here, so I took out the negative sign. And then I add 1 and minus 1. Basically, exactly the same thing. But you have another practice then. Now, in the end, I should put k first and then the square second. So I swap these two terms. I put 5 first and then the square second. That's the answer. That's the first part. The second part, that with this particular shape of function, this shape, that is something minus something squared. Now, this example is something plus something squared. I think they are different. This is something plus something squared. This one is something minus something squared. In this case, I should use this substitution. That is, this value equal √5 sine theta, and theta is between -90 to 90. That these two endpoints are not included this time because of the denominator. And then when you put it in, and this is when you need to decide whether or not the square root will give a negative value. I think I said it wrong. Probably why Sophie is asking me, how can this be a negative value? Now, perhaps I said it wrong. Now, it's this. With the square root cosine squared. Now, you think it's equal to cosine theta only when theta lies in quadrant 4 or quadrant 1. Now, if theta lies in quadrant 2 or quadrant 3, you cannot say this is equal to cosine theta. Why? Because cosine theta itself is negative. In this case, it's negative. This value itself is negative. So if I want this to be equal, I have to automatically add a negative sign to make this positive. Do you know what I mean? Now, I'm not saying that this square root should give you a negative value. I'm saying that when simplifying, whether or not you need to add a negative sign to make the outcome positive. And in this case, you don't have to, because cosine is positive in this case. Let me say it again. In this simplification, because cosine theta is negative itself, in the simplification, you should add negative sign to make the outcome positive. But it's not the case in this question. In this question, theta is not. I'll just leave it there because it's not the main part of this lesson. It really is not. If you have further question, I'm happy to answer you. But right now, with the principal value involved, you just simplify as the cosine theta, cosine theta. And then you get the answer, and then you express the answer. Is that okay? So that is the lesson. Again, if I throw away this whole thing and we just completely ignore this, I think in terms of the skill, you're not losing anything. In terms of integration skill, you're not losing anything. It's not like you cannot do it. You can still do it. Just it's one thing. It's not completely clear. It's not as your math teacher, I have to tell you. It's because it's decided this way, but you don't have to worry too much about this. Okay. because I have to, this has to make perfect sense. If it doesn't, then I'm doing it wrong. I have to tell you. So what you really need to learn in this lesson is when to use this substitution and when to use the other substitution. I think the method is in the title. When you see different things, you use different substitution. Okay, it's in the title. Now, when you see this or this, you use the sign substitution, but it's not like x equals sine theta. It's not. It's always like x equals something times sine theta. Okay, it's not equal sine theta. It's something about sine theta. And with the other one, you see a square plus another square, and then you use tangent. Again, it's not tangent, it's something times tangent. In your exercise, that if you all the exercise, you should intentionally practice this method. Now, I'm not saying that some of the exercise cannot be solved using other methods. Now, with the examples, it's perfectly fine, because example 22 and example 23, example 24, these three examples, you really cannot solve the integration if you don't use the substitution. But in your exercise, some of them, it's maybe easier to use another method. Maybe it's easier to use another method, but because we want to practice this method, you have to intentionally use this method. Okay, so that's all. That's all. I'll see you on Monday. If you don't have any question, you can leave now.